Dr. Michael Ajao olarinoye was a PhD student at Coventry University, but he graduated last year, if I'm right, and now he's doing a postdoc at Coventry University. He is going to talk about algorithmic training strategies for physics-informed neural network wall shear stress prediction in cardiovascular hemodynamic. Mikhail, please go ahead.
Okay, thank you. Thank you, Dr. Amir. Thank you for inviting me to give a talk. So good morning, everybody. My name is Michael Ajao olarinoye, and I'm going to give a talk today on algorithmic training strategies that I discovered doing some of the work with the group from now Professor Asif Mohammed in NUST. And we worked on a few things. So I just wanted to present some of the particular specific findings and some of the useful training strategies that I discovered to be able to come up with quick and good solutions. Okay, so I'm going to present the 4 case studies we worked on, and I'm also going to show you some of the results, some of the challenges that we went through, what the data was like, and how we ended up solving some of those problems. Okay, so just to start, wall stress shear, some of you might know quite a lot about it, but to be very specific, it's wall stress shear itself is not the problem, but cardiovascular disease is quite a very rampant thing that needs to be solved. So detection or early detection of it by any software is well accepted. So to be able to understand the effect of it, like about 92 million adults in the US alone suffer from various types of cardiovascular disease, and which of course is quite dangerous. And also the abnormal wall stress shear value being low, it promotes heterostatics plaque growth. Now, uh, what are we just talking about? We're just talking about the flow of blood through most of the blood vessels in the heart and things circulating around the heart. Okay, so as an example, or what people have been working on. So there are models, vascular models that you can find online or taken by a real patient that shows the way the structure of the arteries and veins, or for example, if you want to add a graft, the way they are. Now, most of these models are CFD produced. Now, it takes quite a while to be able to generate some of this geometry and meshes for the CFD. And the thinking was, are we able to then build a neural network model that learns the sapiotemporal structure of these CFD models and then generate close to or exactly what it is at inference time? So another example is diameter-based rupture risk failures. It occurs about 5.6 in men and 11.6 in women. So the diameter of uh, most of the vessels matters a lot, and some are usually fall below 5.5 and 5.2 centimeters in terms of the threshold. Now, there are various markers that we can use to determine what the threshold is, how large a vessel is, and so on and so forth. So most of the markers that we tend to use are the OCI markers or the wall stress shear patterns. So specifically, I'm going to be focusing mostly on the wall stress shear patterns, looking at the velocity and sometimes the pressure outcome of it. Now, this is provided via the superior prediction. And the question is, can we, like I said, train a neural network on a fraction of this data to be able to recover the wall stress shear at inference costs to see how well the neural network models can be? Now, so most or some of the models that we got were done in steady state, so you have to generate them in a CFD solver, and this produces or some of the results we got to a steady state, and some were transient state. Now, it would have been nice to have more snapshots of what of each of the states to be able to regenerate or recreate a very nice flow. but sometimes just having two snapshots is quite enough. Now, for this aspect, you have a CFD solver. You also have to generate the mesh. You need to understand what the blood flow mechanism was. You use Cardiovascular equations. You use RANS equations. So on and so forth. You need to understand the turbulence, the boundary conditions, and what cardiac cycles each of the states is in. Now, the data produce usually about 800 wall points, and the data tells quite a lot of story for us to then be able to use that in modeling it. Okay, so I don't know if everybody knows about physics-informed neural network, but I think it's a very common method as of now, and it's relatively there are um, so many libraries that you can use to solve this problem. It's a neural network that learns data and also optimizes the gradients of the equation, and then using that with the loss function to generate the prediction. Now, the residuals of the PDE, right, which of course got via automatic differentiation. And like I said, there are so many libraries you can use to do this: PyTorch, DeepXD, so on and so forth. Okay. Now, the important thing about this talk is how do we optimize the loss function, because the loss function comes with so many things involved. So the loss function has to have things like your Navier-Stokes momentum and continuity residuals, which are gotten from the automatic differentiation at a certain collocation point on the data which you subsampled. You also need your wall stress shear losses. You need your data loss. You also need the data loss is gotten at certain sparse point in a wall sample, and you need your boundary condition losses in some cases, right? So some things like your inlets, your outlet boundary condition, things that we use to create data in that instance. Now, uh, how do we now then balance these losses? This is where this talk I'm about to give today is going to show you. So the four case study we worked on used some various things we've learned, or we found out that other researchers have researched to make it work. And the work was based on a paper from Azani et al., where they used sparse points to be able to generate predictions of the wall stress shear at a certain point. Now, the governing equations that combine most of these studies in the works we did, mostly the mass conservation equations, the momentum, Navier-Stokes, momentum and continuity equations, your Carrier-Schiller non-Newtonian viscosity, and also, of course, the wall stress shear. So I'll show you the four different um, case studies, like I said. And two of it are currently published, two are in the pipeline to be published. And so, why the solving pins for most of these problems? Why do we need to solve the hemodynamics using pins for most of this problem? And why are they hard? Now, like I said, the work was built on work from Azani et al. What Azani et al. Was able to discover was you're able to use pins to solve uh, to use pins using sparse data to solve a certain problem. Now, it meant that just using regular MLP, okay, sometimes learns the low frequency and usually what stress share lives at the high frequency. So to be able to then get the specific data or the specific sparse point, we need things like spectral bias. No, spectral bias actually occurs. So we need things like how do we now then take the initial learning rate or learning stage of the neural network to get the data from the high frequency part. Okay. Now we also have multi-scale issues, and you also have computing losses issues where the data loss might be bigger than the physics loss, or the physics loss might be bigger than the boundary loss. You also have things like does geometry generalize to each other. So like I said, you can have data points for different diameters in centimeters, right? So do you then take a model trained on 5 and then transfer it to get that of 6? And also the boundary condition enforcement on curved walls is quite unique, that it is unique to each patient specific data. So you're going to see how some of these were solved in some of these cases. Now, the 4 case study, the first one is a thoracic aneurysm study, whereby we got data from 6 different patient-specific ones, both LD and diseased version. And also the flow part of it was, we used the Rance equation, and it was pulsating at systolic and diastolic, and also use the correction Yesterday equation for this. Now, the algorithmic contributions that we made to this particular work was, we used the gradient norm algorithm to balance out the weight of solving the physics informed equation. We also made use of a dual optimizer technique, whereby we're optimizing 2 different neural networks together to get a certain outcome. And we're able to learn the velocity and the viscosity aspect of it also. And we also worked on the transient pains that looked into Marfan syndromes and so on and so forth. That one had the 7 neural network ensembled styled a model, and what we used for the learning for the loss for learning the loss is the learnable log negative form of it. And for the double thoracic pains, we had a steady state flow, and we used ResNet. I'm pretty sure some of you are familiar with how ResNet work. We use ResNet, the Fourier transform for the spectral bias aspect of it, and the data-driven non-dimension way of standardizing the data. And also we then derived the wall stress shear from the velocity equations. And for the grafts, CBGA pins, we had 12 specific patient data at 2 diameter centimeters. So we had steady flow equations for that. We used the unified Fourier pins for this particular one, and the equations for this that were solved with the Newtonian and the Yesterday equations for that. Okay, now the first one, like I said, is the TA aneurysm, which is the thoracic aneurysm problem. And so from what you can see, we had a Fourier feature encoding for the spectral bias. The data that is taken is the sapiotemporal CFD data, and it is just taking the sparse point of that data, so about 20% or 10% randomly sampled at every given time. So we have your X, Y, and Z, and also the 2 phases because it was transient. Okay, so we're able to build a network that predicted the velocity, the pressure, and also the viscosity, the learnable viscosity. So what the model was able to do is to train simultaneously and solve the velocity and pressure, and also the learnable eddy viscosity on its own from the network itself. Now this was then balanced using the losses from the data, from the boundary condition, and also from the automatic differentiation of the equations to get a good result. Now the neural network itself just had an input layer, a Fourier layer, then a linear layer, and a switch activation function, which used a learnable beta parameter, and each of that was then stacked in the ResNet style block of about 6 to 8, and then a linear output layer to produce the outcome. Now, the model was able to produce a wall stress shear out to values of about 0.86 plus or minus that across the 6 geometries that was trained on and evaluated upon. Okay. So the actual loss weighting technique that was done for this case, it was the Grand Norm EMA adaptive weighing techniques. And before we move on to the next project, and that allowed us to be able to then get the right balance and train the model uh, in and train the model in a relative time to be able to estimate what the outcome would be. The particular GPUs that we used to train these models were the RAT ADA RTS ADA 8000 GPUs, and this produced quite a good result. So the two phases, like I said, were the systolic and diastolic, and we were able to generate the actual systolic and diastolic representation of what the CFD would have been as a surrogate model. Now, the next project was the transient pulsating pins work, which had six aortic models. So four were those with the Marfan syndrome and two LD syndromes. And we trained 7 independent pins for this one. So this one, each of the parameter, the pressure, the velocities at each point, and also the wall stress shear had its own pin network trained simultaneously together. It had about 10 layers. Each of the layers had 64 in state. And we used also, like I said, a learnable switch activation function. So I discovered that the learnable switch activation function allowed the neural network to actually converge very fast, very quick to what the points were. And this particular one had a batch norm layer to each one of it also. Now, the learnable log multiplicative weight was used to balance out the loss training, which was very important by Adam W. Now, the pulsating inlet was enforced at a loss time to show that it being asystolic and diastolic. And the paper is currently published in Fluids of Physics. If you want to have a read, it's a very interesting paper. It was one where we're all happy about the results. Okay. Now, the next work was double pin, which was a steady state. For this, we just used the ResNet and the Fourier block. As you can see, by this point, we've already started establishing what techniques works best, although we were still experimenting with different things. And like I said, this work built on the work done by Azani et al. So most of the things that changed were how the loss weights were optimized, what the structure of the neural network looked like, how to get a faster training time, also faster inference as time also. Now the three double using geometry we use for this project were the 4 centimeter, the 5 centimeter, and also the 6 centimeter. Now, each of these was trained on a ResNet block of 120 dimension for the Fourier embeddings, and we had the 4 output heads. So the 4 output heads were the wall stress shear, the velocities, and also the pressure. Now, this made use of data-driven non-dimensionality aspect to anchor the wall stress shear from the data, and then sampled at the point at near wall point and interior collision point. Okay, this was actually very important to be able to get the specific wall stress shear at the neck of the data itself. Okay, so yeah, as you can see, the predictions of the pins were relatively close to what the actual original CFD generated at each of the aneurysm geometric diameter. Okay, now so these also produce very good results in a supervised learning training way, which is also published. Now the third one is based on a graph example. We're trying to understand or trying to see if we can use the same techniques to be able to get predictions as to the strengths and the wall stress shear ability of grafts on most of these data models. So we had about 12 patient models from the vascular model repository that were trained, and the CFD data was then used. We also used the sparse method for this instance. We used the, like I said, the ResNet pin with Fourier embeddings to help with the spectral bias aspect of it. And these are the 5 outputs, and the worst ratio was generated from the velocity. Okay, because it's very important to get that. So the for this particular one, we were trying to experiment with just using the fixed weight loss that most researchers have been using to see if we can also still get as good of a result as what we were getting with the various loss tuning way. But it meant that we had to manually understand that we gave more reference to the what stress share loss and also the velocity loss and sometimes the data loss. So it's just to see if we can specifically get the specific loss in the fixed way to determine and counter the aspect of most of the adaptive loss weighing schemes I've been showing you. Okay. Okay. So it took a while to train this. It took a while to figure out what each loss weighing scheme should be. It took a while to determine the value of each of the fixed weighing loss, but we're able to regenerate most of the Sapenius vein grafts to a good extent as to what the CFD representation was. And the absolute mean square error that separates both of them was also quite good for what we saw. So for this particular model, it was just a single, rather than a separate set of neural network parameters, it was just a single unified neural network parameter trained on each of it. Okay. Now, the network structure that we've used in most of these projects contain a few things. So the first thing is mostly an adaptive weighing loss scheme. Yeah, it differs project to project, but we always used an adaptive weighing loss scheme. We also made use of the Fourier feature embedding, Fourier feature encoding, which we discovered in some papers around advances in pins, to show that getting the data from high fidelity level is quite good and important. And yeah, so for the Fourier feature embedding, okay, so what we do with this is we map the raw coordinates, okay, from the actual feature embeddings from randomly, okay, before we then pass it into the neural network structure that we currently have. So this method was gotten from Tansik et al., published in, was presented in the Neural IPS conference in 2020. It's very good to see and understand it because it helps with the anti-spectral bias problem that most pins model are usually get engrossed in or lost in. Okay, so for these particular aspects, for 3 of the projects, adaptively, the Fourier feature embeddings were selected and tuned to the expected feature frequency of the specific data. Okay, and you mismatching the alpha part of it kills whatever worst ratio prediction you get at the end of it. Okay, so okay. Now the next one is the gradient norm EMA adaptive weighing scheme. Like I said, and the algorithm for this requires your losses of data, the worst ratio, the boundary condition, and whatever losses you've modeled in your equations, and also the parameters from the neural network and the weights from the neural network. And now, then we take most of this and generate the mean of the gradient norm, and then use that to solve for each of the parameter losses at each of the epoch. Okay, now for this, we used it in the TA project, like I said, but the original method for gradient norm was gotten from Chen et al. So we adapted it to the particular problem we had and extended most of the losses that we could use it to adaptively tune. So The mean absolute gradient norm is very important because that's what we need to generate for each of the loss term. And adaptive predictions, as you can see, the physics loss reduce gradually based on the number of epochs, although most of the epochs we trained most of the problem on were about 10,000 plus upwards. Now you can see the gradient or the improvement of the physics loss per epoch based on it. You can also see how it does with the water stress share loss and also the inlet and outlet boundary conditions and also the pressure along the way. Same can be said for the adaptive weight also, because we tested them to see what they output with. So the weight was changed after each epoch based on what the mean absolute gradient norm value is. Okay, then third one is a self adaptive learnable log, which we use in the transient problem. Now, the self adaptive learnable log, I discovered it in a research paper, and the way it work is we take okay to make every loss weight trainable parameter. So each of the loss weight itself, right, the one from each of the loss weights that we have. Let me just take it back there. So the loss weight for the water stress share, the pressure, the inlet, the outlet, the physics, each of those specific loss weight, we made the neural network itself learn and adapt to it per every epoch. Okay. So I'm here. So what that meant that was that we were able to move from using fixed weights in the CABGA problem to the grad norm, EMA, adaptive algorithm in the TAA, and then the learnable self-adaptive weight in this particular problem for the transient one. And it showed that using learnable adaptive weights for learning the losses in the neural network is quite effective most of the time for most of the problems you're trying to solve, because the trick is to find what specific value the fixed weight should be to get you to the point you want your models to put what you want your models to produce. Is quite a hard problem to solve. Okay, and this stops the physics problem from decaying out of the optimization entirely, which is one of the things we discovered when training most of this model. That the physics sometimes either tries to dominate or decay very quickly out of it. Okay. Now the collocation sampling that we use for some of these projects, we had the uniform interior sampling under using the boundary layers where the water stress share is defined. So for example, I'm just going to quickly take it there. So for example, this is a 3D model of one of the data set of an LD1. Now the water stress share is mostly defined at a certain point in the geometry, and you can also see that all around what we have. So if we're able to then sample at this point to be able to generate the full geometry and sample at the interior point and also the exterior point, given the boundary conditions of the inlet and the outlet, and also given the boundary conditions of the full data, and sample at random points in it, we're able to then produce what the specific water stress share parameter is going to be. Okay, so we're going to go back to the other slide so we can move on very quickly. Yeah, so the collocation sampling is a very important problem to solve in most of this problem. And we usually try to find a solution to it using things like the surface normal computed via the open 3D to get the radius of a PCA. Or sometimes we empirically just try to determine what a mesh inside the model would look like. Okay, so I'm guessing I'm close to my time. Now we also have things like network topology. How do we determine that? And the usage of dual optimizer. So importantly, solving two neural networks sometimes is also a very quick way of solving a problem rather than sticking it into one neural network. So things like that. We had an algorithm in one of the papers that is also published. You can read it. And we add things like how to anchor the physics part using non-dimensionality scaling rather than the normal standard or min-max scaling methods that we use. And it's very important that the WSS tangential projection is quite good, which we discovered from, like I said, the Azani et al. Paper on using it for computational physics. Okay, I think I'm getting to the end. So we got good
Yeah,
results for most of these
I
projects,
think
and
I
which is
think we
one of the
should
important
end
things.
it. Okay.
Yes. So to end it,
Uh,
we are just thinking out to now the next method, which is mostly to transfer at getting using one geometry to be able to predict another geometry, which is a very important thing that we are trying to look at now. We're able to replicate each of the geometry, but now can we train it on one and then use that to estimate the other geometry from it and also get like a real-time sample of systolic and diastolic predictions from PIN. So thank you, everyone.
okay,
Thank you
thank
so
you,
much.
Dr. Mikhail, for the presentation.